when it rotates around the center of rotation D, it will cause a clockwise rotation. Yeah, it's going up, so around D will be a clockwise rotation. So clockwise rotation is positive, so we put a positive sign there. Okay, so then the other force, yeah, on the right of VB is 7.5 kilonewton, and again this will cause a anti-clockwise rotation around D. So you can see all the forces which are going down are causing anti-clockwise rotation around D, because D is to the right of these forces. If the center of rotation is to the left of these forces, all forces going down will cause an anti-clockwise rotation around the center of rotation. Okay, so again 7.5 kilonewton will cause an anti-clockwise rotation around D, so that means that we have to put negative here. This moment force is anti-clockwise. Now for VD, it doesn't really matter whether it's clockwise rotation or anti-clockwise rotation, because there is no distance between VD and D. So we can just put here plus or minus VD, and this whole equation is equal to 0. Okay, so now let's just rewrite this equation here. Okay, VB or 9VB equals to 80 plus what is that, 56 plus 4 is 60. Okay, so that's 140. So VB is equal to 140 divided by 9. Okay, that's 40 divided by 9. Just using my calculator there. That's 15.6 kilonewton. Okay, because this is a reaction, so it has to be kilonewton. Yeah? Reaction is a force, so the unit for force is kilonewton. Since here we are using kilonewton. Okay, so now let's use the second equation here, which is sum of all vertical forces equals to 0. Okay, sometimes I will use V, sometimes I will use F, y equals to 0. Okay, so it's the same thing. Okay, and then we use the notation that any force going up is positive. Alright, so starting again from the left to the right, the first force that we see is 8 kilonewton going down. 8 kilonewton going down, so we'll just write there 8. Okay, and then we have VB going up, so VB we write there. Okay, then the next one is 7.5 kilonewton going down, so we just write 7.5 kilonewton there. And please bear in mind that we just write down the force, we don't multiply by any distance. Like for a sum of moments, we multiply the force by the distance. That is because it is moment force. But in sum of vertical forces, we do not need to multiply the force by the distance, just the force itself. Okay, after 7.5 kilonewton here, the next force is VD, so we just write VD there. Okay, and the whole thing here is equal to 0. So now we need to put in the plus and minus. So 8 kilonewton is going down. We have a sign here which says that any force going up is positive. So this 8 kilonewton is actually negative. VB is going up, so that means it is positive. 7.5 is going down, so that means it's negative. VD is going up, that means it's positive. Alright, so we already find that this VB is 15.6 kilonewton, so we just put it in here. We have minus 8 plus 15.6 minus 7.5 plus VD equal to 0. So therefore we can calculate VD equal to 8 minus 15.6 plus 7.5 equals to, let's calculate that, equals to minus 0.1 kilonewton. Okay, so it is a very small force actually here, very small force, and it is actually going down. So what's happening is that we have a bit difficult to draw this. Okay, we have this force here, and with this force is actually 0.1 going down, and this force is 15.6 going up, and then we have this force 7.5 going down. And remember that this is a UDL force, which is 2 kilonewton per meter. So we have to restore back this UDL force. Actually it is a UDL force, not a point load, because initially we changed this UDL force into a point load. Okay, so the condition is like this. Okay, we have a big positive reaction here going up 15.6 kilonewton, a very small or almost zero reaction here going down 0.1 kilonewton, point load 7.5 kilonewton here, and a UDL load. Yeah, maybe this UDL load is like a brick wall, 2 kilonewton every meter. So this is the solution.